The behavior of a gas can be described using a pressure versus volume graph. What kind of graph? And what do you mean by the behavior of a gas? And how can we have this thing, this diagram for a heat engine, how can we have that explain a real engine? Well, here's a gas. It's kind of like a mosh pit, all these elastic collisions, the ideal gas model. Here we have an equation for the total thermal energy of the gas here, the sum of all the kinetic energy of all the particles. It's equal to 3/2 N, capital N, the number of molecules, Kb, Boltzmann's constant, times T, temperature in Kelvin. We also had an equation from last time for the root mean square velocity. There's the equation. Not all the particles are moving at the same speed, but this gives you some idea about a common velocity. And as you see, temperature is pretty key. When temperature goes to zero, motion goes to zero, velocity goes to zero, energy goes to zero, absolute zero. But there we have all those particles happily bouncing around, and we can talk about the pressure. Pressure is equal to force divided by area. We can talk about the pressure that this gas exerts on the walls of the container. Now, how could we change that pressure? Here's one way. We could increase the temperature. Increase the temperature, and you're going to increase the pressure. Why is that? Well, where do you think the pressure comes from? Pressure comes from force divided by area. Force of those collisions. We're back to collisions now. Increase the temperature, to increase the speed, increase the number of collisions and the violence of the collisions. Now you're talking about pressure. There's another way to increase the pressure, another way to increase the number of collisions, decrease the volume of the container. A smaller container, walls are closer, more collisions, more pressure, more force per area. Or, final way, increase the number of particles, a greater number of particles, and you will again have more collisions, more pressure. So there it is. PV equals nRT, the ideal gas law, which says what we just said. To increase the pressure, you can either decrease the volume or increase the N number of particles or increase the T, the temperature measured in Kelvin. R is just a constant. 8.31 joules per mole Kelvin. Uh-oh, I said it. I said the M word. I said mole. Don't worry, if you hate moles from chemistry, we won't talk too much about moles, but small n stands for the number of moles of gas. In our earlier equation, we had 3/2 NKBT, where capital N stands for the number of particles. Now we're talking about small n, the number of moles. And you know what? Those equations, they like one another. They can be harmonized one with another. So what you're saying here is that R, the ideal gas constant, is equal to Kb, Boltzmann's constant, times Avogadro's number. Well, never mind. But I understand this. The nRT looks a whole lot like an energy equation. Looks like we're talking about energy here. Is PV also an energy type equation? Well, what is PV? Pressure is force per area measured in newtons per meter squared. Volume measured in meters cubed. So you multiply pressure times volume, you get Newton meters. Reminds me of work. Work also measured in Newton meters. So PV equals nRT. Rolls off the tongue, doesn't it? PV equals nRT. The ideal gas law is an energy equation, like the first law of thermodynamics is an energy equation. And now we can talk about the behavior of a gas being described using a pressure versus volume graph. Now here is an ideal gas. It's the orange thing inside that cylinder there. Here we also have a pressure versus volume graph, and there it is. There's the ideal gas on a pressure versus volume graph, and here we have some of its friends. We have the blue gas, looks like a big volume. We have the red gas, a smaller volume. I guess that makes sense, a higher pressure too for the red gas. And if you think these colors have something to do with temperature, they do. More on that in a second. First, let's talk about our first isothermal process. Our first process is an isothermal process. That means you make sure that the temperature stays the same. And how do you do that? Well, one way is to put this cylinder of gas inside an ice bucket. You put that cylinder of gas inside an ice bucket, and the temperature of that gas, you can believe me on this, will stay at 0 degrees C. So that's a good way to have an isothermal process. And then you can compress that gas isothermally, and you will draw a curve on this pressure versus volume graph, that curve known as an isotherm. And here we have some other isotherms. So one thing we can notice here is that the closer to the origin you are on a pressure versus volume graph, that means a lower temperature. Makes sense. Small pressure, small volume. We're talking about energy here, small energy, small temperature. far away from the origin. On the upper right, you could say that means a higher temperature. A higher temperature gas. If you have a big pressure and a big volume, you got a lot of thermal energy inside that gas, a very energetic gas. So that was an isothermal process. Those are some nice looking curves there. And next you can talk about an isovolumeric process, making sure that the volume stays the same. This one might be a little bit easier to do. You don't need a bucket of ice. All you need is a lock. Put a lock on that cylinder. Don't let it expand or collapse. And what do you do then? Well, you can put a flame. You can put a flame next to that gas and you can increase the temperature, and that means that the gas on the PV graph will do this. Just like we said, it will increase in temperature. It'll get farther away from the origin. On the pressure versus volume graph, that is isovolumeric heating. Nice to see you. The next one, isobaric. Isobaric means the same pressure. Make sure that the pressure stays the same. How do you do that? Pressure is force divided by area. So you have the same weight, same area, same force, same flame from the last example, and then we are going to allow this gas to expand as it heats, but its pressure stays the same. So again, the temperature is increasing with this isobaric heating. Not the same as isovolumeric heating, but in both cases, yeah, we heat it up, so yeah, we are increasing in temperature. One more ideal gas process to talk about, and that is adiabatic. Adiabatic, by definition, means no heat is allowed to enter or leave the system. You could do this with a well-insulated cylinder, a good cooler or something like that, a good insulation, or a better way to do this is just do it real quick, like have a force compress that gas faster than you can believe. Just push down on it really fast. There is no time. Time is our friend here. No time for convection, conduction, or radiation to give you a cue. Here we have higher pressure. We have a smaller volume, but we also have an increase in temperature. Did I say heating? No heat allowed to enter or leave the system, but we have an increase in temperature. No Q, but an increase in temperature. This is the first law of thermodynamics at work here. We have an increase in temperature without allowing Q. It's delta E is equal to delta W plus delta Q, and we had a delta W, therefore we had an increase in thermal energy, an increase in temperature. One more thing about an adiabatic process, and that is that the work done on the gas, increasing the energy of the gas, increasing the temperature, we did work, and work is equal to the area. The work done on the gas is equal to the area underneath the pressure versus volume curve. So there they are, isothermal, isovolumeric, isobaric, and adiabatic. Our four favorite ideal gas processes. Each of them obeys the ideal gas law. PV equals nRT, pressure times volume, is equal to small n, the number of moles, times the ideal gas constant, 8.31 joules per mole Kelvin, times temperature in Kelvin. Remember, when we're talking about temperature in Kelvin, that is related to the total thermal energy of the gas, also related to the velocity of the ideal gas particles, but E thermal, that's a thing. First law of thermodynamics, also definitely a thing. And let me say just one more thing about this W character. We said in the last video that you could do work on a system by compressing that gas. The gas will gain energy and warm up. Here that is in a PV graph. Volume is decreasing. We are going to the left on this PV graph, and the gas is warming up. All other things being equal, an adiabatic process being assumed here. Or you could have the gas expand. The gas expands. Work is done by the gas on the surrounding. You could imagine the gas expanding and shooting a pellet up into the air and losing kinetic energy, and the pellet gains the kinetic energy when the gas expands. Adiabatically, the gas loses energy and cools. It moves to the right. In this case, we're moving to the right on the PV graph. So if you're moving to the right on the PV graph, the delta W for the gas is negative. You're losing energy as the gas. I mean, everybody else likes it because you're giving away energy, but for the delta W for the gas itself, delta W is negative if you're moving to the right on the PV graph. Delta W is positive if you are moving to the left on the PV graph, which we'll need as we attack these 1, 2, 3, 4 ideal gas processes, starting with isothermal. Isothermal expansion and compression. Well, since they're isothermal, the total temperature stays the same. That means the total thermal energy stays the same. There we have it, and the first law of thermodynamics still a thing. So for this isothermal expansion, delta W is negative. and delta Q is positive in both cases here, whether you have isothermal expansion or isothermal compression, the magnitude of the W and the magnitude of the Q have to be the same because delta E thermal is 0 by definition for isothermal expansion. Yep, we're moving quick and we're moving on to isovolumeric heating. Isovolumeric, what does that mean? That means that you don't change volume. Well, if you don't change volume, you don't do any work. Now, how do you know you didn't do any work? Well, you didn't do any work because there's no area underneath that vertical line. Delta W is 0 in both cases. Are you moving closer to or further away from the origin? Isovolumeric heating, you're moving further away from the origin, so delta E has to be positive. You are increasing in temperature and thermal energy. And if delta W is 0, then for isovolumeric heating, delta E has to be positive and delta Q has to be positive. And in this case, the magnitude of delta E has to equal the magnitude of delta Q because nothing else is happening. So there's isovolumeric heating and cooling. Another example, here's a good one. Adiabatic expansion, adiabatic compression. We start here with the definition that delta Q has to be 0. That's what makes it adiabatic. So there we have it, fairly straightforward. Now, if you're moving to the left, you got a positive delta W. You're moving to the right, you got a negative delta W, adiabatic expansion. Like we said, gases expand, they cool off adiabatically. Gases are compressed, they warm up. They have a, can I say that? Can I say they warm up and cool off? Does that indicate a Q? Again, this sounds weird. Every time I say it, it sounds weird, but your temperature is changing. No heat is gained or lost. Can I say cools or warms? I'm not sure. I'm morally conflicted about that. But we agree that the temperature changes. No heat is gained or lost. There's more than one way to change the temperature. You can do a delta Q type thing or a delta W type thing. And if you don't believe me, just take your two hands. I'm sure they're at the same temperature and rub them together like that. Delta W is positive and your hands will increase in temperature. Now, do they warm up? That's a philosophical question. One more. And this is the worst. This is isobaric expansion and isobaric compression. This is a tough one. We'll start with delta E. Well, delta E is positive for isobaric expansion. How do I know that? You're moving further away from the origin. So isobaric expansion has to have a delta E is positive, but you're moving to the right. And we said if you're moving to the right for isobaric expansion, then delta W has to be negative. Has to be negative because the gas is expanding. So delta W is negative. Now we said that under all else being equal, we expect if delta W is negative, if the gas is expanding, we expect it to cool off, but not in this case. Not in this case, because in this case, the gas's temperature is increasing. And how is that possible? Only if there's a delta Q, only if there's a big delta Q. And in this case, we see that the magnitude of delta Q has to be greater than the magnitude of delta W. See that? The magnitude of delta Q has to be greater than the magnitude of delta W in this case. All right, I guess it kind of makes some sense here, but I have a question for you. Who could ever possibly care about any of these four processes? And the answer, I hope, is maybe you, especially if you are familiar with the internal combustion engine. How does that work? Well, let's take a look. Here we have the internal combustion engine as promised, and we start with step 1, the cool air intake. We call this the cool air intake because cool air comes into the piston. All right, that's good. How about step 2? Adiabatic compression. We know about adiabatic compression. The piston is compressed and the gas increases in temperature, and so far this is a very lousy engine. So far this is a very lousy engine because it hasn't given you anything. In fact, it's required work. You have done work on the gas and you're thinking to yourself, this better work out for me in the end because so far I've invested energy compressing that gas. It hasn't even said thank you, and there you go. But step 3 is the big step here. We have ignition. The spark plug sparks and the gas changes temperature very rapidly. The gas changes temperature very rapidly, but notice so far at least we haven't changed volume. We have, what would you call that? Volume stays the same, but we'd call that isovolumeric heating. Isovolumeric heating. And now we have increased pressure. Yes, increased pressure. We have a really high pressure. Let us have step 4. A power stroke, adiabatic expansion. adiabatic expansion, and there you have it. And remember that the work done is the area underneath the curve, and that means that the more work is done for step 4 than it was for step 2. And there we have it. And then step 5, exhaust, and we're ready to start it again. It is a cycle. Here we have a cycle. The piston is going up and down and up and down, and here we have a cycle. And we can say that the area underneath that curve, or inside that curve, however you want to say it, the area there is equal to the work done by this cycle, the work done every time the piston goes through this cycle. QH, what is QH? That was a mystery. What is this QH? Well, QH is the chemical energy delivered by the gasoline. The chemical energy delivered by the gasoline, just like we see here on this heat engine diagram here. And then we have QC. What's QC? QC is the energy lost to the exhaust, the energy lost to the cold reservoir. Notice again, we said this, you're always going to lose some energy. It'd be nice if your exhaust was at absolute zero, but it's not, and therefore your internal combustion engine cannot be 100% efficient. And there you have it. And if you're thinking that that was okay, but just a little bit too qualitative, check out part 2.